Today we have Mikkel from Grundfos, and he is the chief data scientist at Grundfos and data and AI. He holds a master's degree in physics and also a PhD in mathematics. So he's also one of he's a member of the standardization boards in Denmark, one on AI and on industrial data, which we will learn in a bit from him. So Mikkel, thanks for joining us, and the floor is yours.
So hello, my name is Mikkel. I'm from Grundfos, as E said. I work as a data scientist and an ontologist and sort of a standardization nerd in Grundfos. I would like to sort of report on some work we've been doing in the last year or so, while establishing the ISO TC 184 Subcommittee 4 Working Group 26 called Industrial Data Ontology. I've been sort of part of making a use case for that called Pump with Firmware, where we have a referenced web of things. So I think that's why E wanted me to come here and talk. And the use case is about IoT operating instructions. So it's very much about web of things and the things you work with, I think. So I'm not alone in this. You see a lot of people here who has contributed, Caitlin and Johan and Maya and Melinda. So I have to praise them also. So what is IDO, the Industrial Data Ontology? So it's actually part 3 of a multi-standard arriving under ISO, and it's about industrial data. It's an ontology for representing industrial data and information, building vocabularies, and manage asset models that employ reference data libraries and exploit reasoning. So it is derived from other sort of standards, and it was formerly known as ISO 15926 Part 14, and maybe someone has used that before. It has actually been put in place into several industrial projects, and this IDO community grew out of that community, and we owe a lot to that standard. It has now been deleted from the ISO 15926 series, and we have sort of taken over. It has been used a lot within the oil and gas industry, and that's sort of logical because 15926 was about oil and gas and process plants. But we are sort of taking it out and using it also in Grundfos, for instance. We use it for industrial discrete manufacturing and so on. It has it's a standard. It's a semantic web ontology. It has 54 classes, some data type properties and some object properties. And you see here to the right, you see some of the, I'll just turn on my laser pointer. You see the class hierarchy. So it's not like a huge ontology. So I will sort of present the use case, and the use case I can sort of motivate it by a use case from our world of water solutions. It's a little contrived and thought up, but I think it holds water. So here you see a ranch in the United States called Bar X Bar Ranch. It's near Wilcox in Arizona, and that place, it has actually groundwater pumps in the ground, pumping water. And there's some software in a PLC that does some intelligence on how to control this facility, because sometimes it wants to pump, it should pump water to the livestock so the cows get water. And when they have enough water, when the sensor in the water throws, they say that, okay, there's enough water, then they use water to irrigate the vegetation, because part of this system is also for battling some of the drought out there and the very dry conditions and trying to re-establish vegetation out there in general. So there is this intelligence about where to pump. And that's exactly the things that Grundfos and our teams has been working on, making cloud solutions that do these kinds of things. But it's not simple to manage all of the IoT equipment that goes into such a kind of solution. So this use case is about that. The irrigation business of Grundfos is organized under the water utility division. And one part of Grundfos utility makes pumps for irrigation, and a whole different team makes cloud solutions that take advantage of these IoT capabilities of the devices. These two teams are sort of the people who produce embedded software and the people who make cloud solutions. They are actually sort of far apart, both physically and maybe also mentally. So they don't always convey and hand over the information about how to use what we call e-products very well, or at least they didn't used to do it. So this is one of the things that has been a hurdle to get these kinds of intelligent water solutions up and running. So I think Beecham Research around 2020, they concluded nearly 3/4 of IoT projects won't be considered successful. So what is it that's so hard about making IoT solutions? And I think one of the stumbling blocks is actually operating sort of instruction handover from the manufacturers. Here to the left, you can see our embedded software as the manufacturers to the sort of solution developers. Our team was sort of tasked with making this a little better and sort of strengthening this information handover. And around 4 years ago, I started looking around, okay, how can we then, what kind of things are there out there? What solutions are there out there for moving data from about how to use IoT equipment? And I found the Web of Things standard to be very useful. And we based our internal sort of IoT device database on the thinking of Web of Things and on the sort of how these works. We don't have, I have to be honest and say, we don't have exactly implemented Web of Things as the backbone solution yet, but we are sort of able to construct a Web of Things files from our database because we are using the same kind of thinking in our setup. So here the idea is that the Web of Things file would be the information handover from the embedded software that tells the cloud solution people exactly how to use a given device and what functionalities, what affordances can it actually use, can it deliver when talking to the cloud, without sort of going into the detail of exactly how it's implemented on the device. So now I would like to switch to the IDO model that we have made that sort of fuels this system, and that's also the use case. Our goal with this use case, my sort of initial thought with this use case was that we want to meet the engineers where they are. We want to sort of figure out how to pick out information from the existing practice of systems engineering. And we want to be able to do this at scale. So in Grundfos, we actually have a lot of types of pumps. We sell hundreds of thousands of different types of pumps. So that means having people being forced to talk to people from the left and the right, having cloud solutions people being forced to call embedded software people, that really doesn't scale when you have that many types of pumps, because you have so many teams that needed to talk. So we needed to do this automated. And we wanted to base our thinking on open standards. So that's why we found things like Web of Things, but also how we found the IDO. Back then it was called ISO 15926 Part 14, as I mentioned. And there's a community around the POSC-CISA association that has released a lot of design patterns that we actually adopted in this use case and expanded upon. That was part of the reasons why we embarked on this journey. And the whole idea is to see how standardized can we actually do the modeling. How can we lessen the dependency of these hero developers that sit and make scripts that make everything work, but then you have a huge risk if these key persons, they get a new job or things like that. So the use case is about a pump with a firmware. So this is just sort of a mental picture to keep in mind when looking at it. And in order to sort of test if the Web of Things file could do what we wanted it to do, we wanted to sort of go all the way to the actual depth of modeling that was needed. So in order to do that, we picked one data property or one IoT data point that had sort of some interesting features that made it a good use case, and that was the liquid temperature, pump liquid temperature. So I don't know if you know, but when you make a pump, sometimes the pump has some electronics, and sometimes it has an IoT server inside it, and it can actually deliver pumped liquid temperature. But often it's not because there's a thermometer directly immersed into the fluid. Often it's actually an estimated temperature, and you are maybe measuring the temperature of, for instance, the housing in this case, because it really doesn't make sense to break the seal of the pump housing. It's hard to keep that seal. So this means that the software side of this story is that in order to report the liquid temperature, you actually have to estimate the liquid temperature based on the housing temperature, and you have to deal with maybe different temperature sensors for different product ranges, but probably use the same line of temperature estimation algorithms and so on. So you have to sort of put yourself in a place where you can organize that complexity. So this means in the language of IDO, it means there are different activities or software processes, you can think of it, going on. There's an activity on measuring observing the housing temperature. There's an activity on storing it locally in a memory where the estimation algorithm can get to it. And then there's a process of estimating the liquid temperature, and then there's a process of observing this liquid temperature out. As you can see here, there's some numbering to it. That's because in the model you'll see 3 different processes. We have sort of bunched together the last 2 processes just to make the model a little smaller, so it actually could fit in the ISO document that was submitted in the ISO draft. So this is an official use case that was submitted to the ISO community in the ISO draft in Paris in the spring this year. The interesting thing about this data point is that it's actually important to know the resolution of the data. So that means, and I'll just, maybe you all know this, so I'm sorry if this is a basic and it feels like a math class, but I will get out of the rabbit hole again, I promise. But the data resolution here is really about how do you represent a continuous number like the temperature in software. And here, just to make it easier to think about, then let's consider what if we only wanted to use 4 bits in the memory of the pump to store the sort of temperature. And this makes sense actually, because you can make a pump a little cheaper if you put less memory in it. So if you can do with 4 bits, then you shouldn't use more than 4 bits, and that's a good design principle. Then you would probably sort of, if you have like a simple way of representing this data, then you could think of 2 to the power of 4, that's 16 different buckets that you can basically only say if your temperature is in one of the buckets. So it's the temperature between the range of 0 to 10 degrees or 10 to 20 degrees and so on. And this means, I skipped that, but the calibration of the sensor is also important. So you need to know what was the minimum temperature the sensor is calibrated to measure, and the maximum, maybe the saturation where it will sort of not report any temperature anymore. So given the range and the sort of register size, you sort of know the resolution. That is, you know how many buckets can I divide my range into. And if you want to keep it sort of a number that is independent on the calibration, you can think about the sort of percentage of the full range that the bucket size fits. So that means each bucket here is about 6.25% or something like that. So you can also think of it as a step size. So I put in here a staircase, so you can really think about step sizes. This is how you get from 0 to 1 in the percentage of range. These numbers you will see in the model, and this is what they mean. So if we look at the Web of Things file that we are really talking about, it's not so much about modeling up here in the sort of the type hierarchy and the product hierarchy. It's more about how do we get these values right, the minimum value, the maximum value, and the multiple of sort of the resolution. So the multiple of is basically what we want to talk about. That corresponds to this step size. So how come it should actually be 1? Maybe 1, it doesn't seem like a fantastic, interesting number, but it's actually really important. Because if you are sitting and making a cloud solution and you are looking at the data and then you see a variation on this sort of the scale, maybe all your data has been put into float, so you don't know that this has been 4-bit at some point. You just have these float numbers coming into your cloud solution, into your C# whatever function, and it could be that somehow, somewhere, some transformation of the data has introduced a sort of artificial resolution of this data. It could be that you get 1.0001, and then maybe it jumps to 1.0005. And is that then a real thing? Or is it just a noise due to the data traffic? And that's actually what this files tell you. If you know that this data is going to be the multiple of 1, then you can ignore that jump. If it's like high precision medical plant you're making, and maybe that jump in temperature is super important and you need to react to it. Sometimes if you tell a customer to react to something, it's really expensive. So this farm, the owner, he could live hundreds of miles away from the station. So if he has to go into his car and drive for 3 hours, you really want him to react to a real event and not to some noise in the data. And this is what this data point can actually help you with. So this basically tells you that these are the data points you should care about. Any smaller change than this is just noise due to the whole sort of transportation of the data from the sensor to the cloud. But this is the important resolution of data. I will now show you the model. In order for it to fit on the slides, we have invented this condensed notation. So you see some bold things in a box, and then you see something that's not bold. The bold numbers and the bold IDs, the bold IRIs, they are actually classes. And what you see here is a small class hierarchy. So you could say this is a way of saying that this E78 is a subclass of the cooling pump class, and the cooling pump class is a subclass of the pump class, which is a subclass of physical artifact. And this list namespace here, it stands for Life Cycle Information System, and that's actually the namespace of the IDO standard. So it has been, we have adopted the old namespace in order for these existing systems to survive. So this LIS, that's the normal way to abbreviate the namespace of the IDO. So I've tried to, in the model, anchor everything in IDO classes and IDO properties. The IRI that's not bold, that's the identifier for the thing. That's the instance. That's the identifier for the specific pump that has a serial number. You can go out, you can touch it, you can kick it. It's a real thing. And in the same sense, you can have hierarchies of properties. So that means if you have this stack in a property relationship, it just means that it's the lowest one that we actually use, but it's a sub-property of consumes and it's a sub-property of has participant. So this is how it is anchored in the IDO standard. Yes. Now for the model. I think maybe I can zoom let's see if I can see this kind of system. Maybe not in this fancy way of sharing. Anyway, so I hope you have big screens, because then I'll try to point anyway. So what you see here is a full model, and we have colored it into different colors just to help you. It's not really necessary for the database to consume it to have these colors. What we have modeled is both some hardware, so that's all physical artifacts you see, and then we have some software. That's the light blue. We also have these activities that I talked about earlier, the 3 activities, and one of them actually has a sub-activity. So we are talking about parts of activities, and that's a very interesting way of thinking. It can hurt a little bit trying to think about it, but it actually works. And then we have some functions, and we have the data that's actually important. And I have just outlined in red the temperature data points as they sort of move through the life cycles. So you can see here in the top right, we have the activity that observes the housing temperature. That's this measurement. And here it's sort of out of that we deliver what we call a profile quantity datum. That's a long history why we call it that, but you can ask me and I'll tell you. Yeah, I don't have to do it now. It will bore a lot of you. And then we generate this first data point here. And here we see we have some metadata on the data point, and that's exactly these relative step sizes. So this is the important bit. This number here, 0.0 something, I can't actually read it, it's so small. But that is the resolution of the data at this stage in the sort of lineage of the data. The data is then consumed in another activity where it is downsampled and stored on the local hard drive, or sorry, RAM, sorry, not hard drive. And here you see it now, it has a larger step size. So it has a more coarse granulation of the data. And this basically just is a sort of a reflection of, initially we stored it in 16 bits, and now we store it in 8 bits. And this is, it's a way of telling the story. What if the pump manufacturer had sourced a sensor in that was born with 16 bits? So that's sort of what you get from the sensor vendor, but you actually only have 8 bits in the memory of the pump. So then you would have to downsample it to fit it into this memory. It could happen. And then there is a sort of the last activity is this activity of estimating the liquid temperature and serving it out. This is where we keep the same sort of step size. And now we also have a metadata where we say, okay, this actually has a web of thing, multiple of metadata that's important at this point, and it's going to be 1. So what is the general rule here? The general rule is that you should not see that this step size become finer. You would not see finer granulation in these software processes when you process data. You should not see this thing going sort of up in resolution as it moves along. It can only be more coarse in resolution or stay the same. And that we can actually validate that. So let me see if I can get to that. And these are some modeling things, but I think I've talked through it. The fun thing is we can actually put this whole graph. I've serialized it and put it into a triple store with the OWL axioms and so on. And then I've made this Sparkle query that then validates what if is all of the software activities, are they obeying this heuristic that the sort of, you see here the produced resolution value is less than the consumed resolution value. Or sorry, this key resolution value should be larger number than this consumed resolution value. This is what you want to have happen. So, and this is how you can actually validate this whole product portfolio and make sure that what you're reporting in the Web of Things file makes sense. So in this sense, you have a sort of a system where you would know how to check what if I change this memory, or what if I change this sensor? Should I also change the Web of Things file, or is it still valid? You can check it using this algorithm. So that was the rabbit hole. I'll jump out now again. So what has this whole system done for us? It's just exemplified how you can pull out different informations about the hardware and the software, collect it in a Web of Things file, and collect it in a Industrial Data Ontology, product ontology, and knowledge graph, and then you can validate these things. And the sort of, we have achieved this value that we wanted from the outset. We can now communicate quality informations from the embedded software development team to the cloud development team using, for instance, Web of Things, thing description files we could generate from this database. We can validate it, as I saw, and it takes actually information both from the hardware and the software perspective to validate this. And if we put this in place, then instead of having sort of PDFs as the documents, we could actually make a database where we can roll out hotfixes much quicker to the digital teams and digital offerings. And this could even be a standard-based system. And we could even extend this because it's open standards, it's World Wide Web Consortium standards and ISO standards. We could actually negotiate a contract with partners and vendors and suppliers and so on, and others, people in the whole ecosystem around the IoT devices could contribute to this model. So that's basically it, what I had. This is what we did. It is in the ISO draft. If you're part of working group 26, you can probably see it there, or else you saw it here and you can ask me for the files. I'll give it to you. Thank you.